Alright, I want to continue on with our little discussion about this slope equation because I didn't want to leave you with the impression that I didn't like calculus. I love thinking about calculus, and here's why. Now remember, just to review, is in order to get, remember this is our equation for the slope of a point at x equals 2 on a curve. And what we do is we draw out our little triangle for x equals 2, and we have this imaginary x, and we imagine the triangle getting smaller and smaller and smaller and even smaller, and here I'm going to go even smaller and triangle that. I'm going to blow up that triangle, and now our triangle, that's a blow up, this is supposed to be a blow up. Now our triangle is so small on this line, that the delta y and delta x are just 4 points on the line. This little triangle now is 4 points wide and 4 points tall, and that's a delta. That's how zoomed in on this triangle we are. X is just, here's x equals 2, and here's our x, and now our x is so close to 2 right here that there's just 4 points difference. And we can go even smaller. Now it's just 3 points different. We can go even smaller. Now it's just 2 points different. Now here is the last time mathematics will make sense inside of calculus. This is the last time. Now I can see if there's 2 points, there's definitely a slope. You can make a slope between 2 points. Notice, if I have 2 points, the slope has to go from this point to this point. There's a definite slope. But if I make the triangle smaller, notice here, from geometry, if there's just the last 2 points on the line, if I make the triangle any smaller, then x will equal 2, and this is what happens. You have just a single point that you're trying to find a slope of. And what does it even mean to find the slope of a single point? Because there's just one point. Like you could draw this triangle in a lot of different ways. It's a single point. You can draw the triangle any way you want. And that red line will have a different slope. Because there's just one point, there's not any single given slope. Furthermore, because of a definition from Euclid, who invented geometry, what a point is that which has no part. So when we're down to this time where x is exactly equal to 2, and we're trying to find the slope of a point, what in fact we're doing, we're dividing this delta y divided by this delta x, and a point is that which has no part. It doesn't have any measurement for delta y. It doesn't have a delta y part. It has no height and it has no width. And so it makes no sense to find the slope of a single point. And look how wonderful geometry and algebra come together, because it makes no sense when we plug in x equals 2 into this equation. The algebra doesn't make any sense, just like the geometry of the height of a point, which has no height, divided by the width of a point, which has no width. It does give you this wonderful divide by 0, just like the algebra says. So it's like a beautiful synergy between geometry and algebra. Here's what Isaac Newton does with this idea. He goes back to the last point where the mathematics made sense. So here, just before x equals 2 here, still this equation, so x is just barely not 2, in fact it's only a single point away from 2, these two equations both say the same number. In fact, this is the time when x is just barely not 2, is the last time these two equations, they're actually equal. And you can do this with your calculator. If you plug in 2.0001 here for x, not 2, 2.00001, and you plug in 2.0001 here, both of these equations will say the same number. In fact, if you plug in 2 and 100 zeros in 1 here, and 2 and 100 zeros in 1 here, those two equations all say the same number. The only problem with those two equations is when you plug in x exactly equal to 2, and then you have to divide by 0. But if you have x equal to just barely not 2, then these two equations are totally fine, and they're equal, and they should tell you, then and only then, these two equations are equal. Calculus is based on claiming that those two equations are in fact equal. And there's a subtle difference, because what we're saying is when we make this substitution for this equation, and we're saying the slope of a curve at a single point is this equation, we're in a sense saying we can't know the slope of a curve at a single point, but we can say just before it got to be a single point, we can know the slope. Both of these equations are the same value just before it got to be a single point. And then it was just 2 points, and the idea is that that's kind of the limit between 2 and 1. The triangle's getting so small that it's just 2 points wide, and then we get to just the limit to 1 point. And calculus says those two numbers, we're going to say that's the equivalent. That's going to be actually the slope. Even though this equation last was true, they were last equal when our triangle was 2 points wide, and calculus is saying this is the slope right at the exact 1 point. And so right now at the beginning of calculus, you should be learning these things about limits, and that's why limits were invented. And notice the interesting language of limits. It's when you take a limit, we won't say x equals 2. We'll say the limit as x approaches 2, to remind you that really we're not essentially making the claim in calculus that x is equal to 2, because really if x was equal to 2, we'd have a problem finding the slope. Also, limits are good for other things, not just slope, but that's why they're important for calculus. What Isaac Newton has done is he has devised a mathematical method for finding the slope of a line at a single point. Now, he had to make some radical breakthroughs, and except his mathematical colleagues probably had problems accepting this line of reasoning, but he in fact did find a method to get an answer for the slope of a line at a single point. And when you do that in math now, that is called, in calculus, that's called taking the derivative. If somebody tells you to find the derivative or take the derivative of this equation, what they're asking you to do is find the slope of that equation at a single point. That's taking the derivative. Now, as we've seen there, what that means, taking the derivative, is finding the slope of a line at a single point. It has some odd implications mathematically, because a point doesn't have any height and a point doesn't have any width. And so, and in fact, that's kind of why we use the word limit to kind of get around that idea. But what I want to share with you is Leibniz, who also invented calculus. He made this wonderful joke that generations of calculus students have found amusing, and I think you will too. So remember, we are trying to find out the slope of a line at a single point, and the only time slope is delta y over delta x is if you have more than 1 point. And the joke is this: if you want to find the slope at a single point, what Leibniz did is he said this. He said the slope of a line at a single point is not delta y over delta x, because a point doesn't have any height. It has no height and it has no width. So the the change in height is really small, so you wouldn't use delta y. What you do use in Leibniz notation is lowercase delta, which happens to look like a D in English, lowercase delta in Greek, and that's because when you see a slope of a single point, it's really small, so you have to use a really small delta. In fact, you use little delta or lowercase delta. And so now, using Leibniz notation, when we want to find the slope, normally we would use the slope of a line, delta y over delta x, but if we want to find the slope of a single point, that is, remember the slope is not very tall and it's not very wide, we would write the slope of a point on a curve as dy over dx, and that's a pun, because points are small, and so to find the slope of a single point, because it's so small, we use small delta. You should laugh. That's funny. That's like, these mathematicians, man, they're a bunch of jokers. If you want to be a mathematician, you have to have a great sense of humor. So this has become calculus humor forevermore in calculus. If you see this symbol, dy by dx, in front of an equation, that means you should find the slope of that curve at a single point, or you should take the derivative of that curve. And that's a joke. That's a pun. That's Leibniz sharing his love of mathematics with you, and that is why I think calculus is just cool. Once Isaac Newton invents the idea of calculus, he goes on and works it, and notice that he now, if he knows the equation f of x equals x squared, he knows the equation right at x equals 2, I know the slope, and it turns out the slope's going to be 4. But doing all that work just to find the slope at x equals 2, Isaac Newton thinks, man, that's a lot of work just to find the slope at x equals 2. And it is kind of a lot of work. And so Isaac Newton says, you know what, I'm going to streamline the process a little bit, and I'm going to do the derivation for not just x equals 2, but x equals any value. And so what Isaac Newton says, let's say I put on the x-axis any value of x, and I'm going to call that value a. And a could be 2, but a could be 3, a could be 4. And I'm going to do the same thing with any arbitrary number on the x-axis, and look how powerful that is. Now, if I know this is my equation, I don't have to do the mathematics for every single possible number on the x-axis every time I want to do it. I'm just going to do it this once, and so I'm going to do the same thing, or Isaac Newton did the same thing. So you find some arbitrary value x, and we're going to make a triangle out of that. And so in order to have the triangle, we need to have a delta y and a delta x. So notice if you go, my equation is f of x equals x squared, and if I want to find the y value here, well, the y value has to be a squared if the x value is a, because this is my equation. And just like before, the x value, this is going to be my arbitrary x, the x value, the y value that corresponds to this x value has to be x squared, because that's my given equation. And so my slope equation is going to be delta y over delta x. The delta y is x squared minus a squared. That's my delta y. My delta x is x minus a. And remember, what I'm going to go for is the slope of that red line, the delta y over the delta x. And just like before, I can factor the top, and I can cancel. And I get slope equals x plus a. And remember what we're trying to do. We're going to find the slope of that red line here as x gets closer and closer to a, and all this thinking and this philosophical thinking that we had in the development of calculus, in this equation now, for as far as calculus is concerned, we're going to just say that x is in fact equal to a, because x gets closer and closer to an a, and then we'll have the slope of this curve right at point A. So here we have x equals a, the slope right at point A is equal to a plus a, also known as 2a. So now I know for the equation f of x equals x squared, for any value on the x-axis, remember I said a could be any value, I just take that value, maybe it's 2, a is 2, and look what I get. 2 times 2 is 4, which is what Isaac Newton got when he tried this for x equals 2. But now I know a could be 1, and the slope would be 2, or a could be 3, the slope right at x equals 3 on this equation, I know the slope of that equation is 2 times 3, that's 6. Now, here's the next kind of funny thing that we do in calculus, and it just strikes me as funny, is because a could be any x value. So all that we do is, instead of we don't leave this equation like it is, since a is any x value, we just say the slope of f of x equals x squared is 2x, because remember we derived a could be any value on the x-axis, and what are our names for values on the x-axis? Well, those are called x's. So then we just go ahead and we change the a to an x at the end. But notice we couldn't start out with the a as an x because we had already an x in our little equation. So there's a little logical kind of joke that Leibniz, and I think Isaac Newton also was had a sense of humor. Both of those guys. For sure Leibniz was a funny guy. Alright, I have a confession to make to you, and I waited this long because all the stuff that I've said before, that's all stuff that you have to know about for calculus. You don't actually have to know any of that except for the lecture quiz, where you have to know 5 questions worth of what I said. And that should be pretty easy. But for the most of physics, you don't have to know any of that other stuff that I said before, but you do have to know this. If you have an equation, f of x equals x squared, you do have to know the slope of that equation for any x is f prime of x. That's what this little tick mark, that little tick mark here, is pronounced f prime of x. And that means anytime you see an f prime of x, that means if the original f of x equation is this, I want you to tell me the equation for the slope of that original equation. And that is what differential calculus is. That's all differential calculus is. Even though now in calculus class you're going to have to do a lot of work understanding why this is true, why this equation is the slope of that equation. That's really not part of physics, that's part of calculus. So all that you have to know is, if I tell you an equation, f of x equals x squared, you have to tell me an equation for the slope. And there's a trick. And sadly, I'm going to ruin some surprises in calculus class if you are just now taking Calc 1. And it's going to spoil the surprise, and I'm sorry, but we have to do that for physics. It's not the best way to learn calculus, because you're going to know all the funny endings in calculus ahead of time, and I'm going to spoil a story for you. Well, and the story is this. Isaac Newton wasn't just satisfied for knowing an equation for the slope of this equation. He also did the same kind of algebra, and the algebra is basically factoring and canceling. And he found the equation for x cubed. And so what he found was, if your given equation was f of x equals x cubed, he did algebra, basically he factored and canceled, just like before. It's kind of harder to factor the x cubed equation, but it's possible. And what he found when he did all this work is the derivative of x cubed, or f prime of x cubed is 3x squared. So what that means is, for any value of x on x cubed, the slope is 3x squared. Now Isaac Newton didn't stop there. He wanted to find out, what if the equation is x to the 4th power? And what he found is that when he did his calculus trick, if your equation is x to the 4th power, doing all that factoring and canceling, and you get x approaches a, and then you change a to the x, just like a joke, then you find that the equation for the slope of x to the 4th power is 4x to the cube. Now, you might start to see a pattern here. Isaac Newton also saw a pattern here, and I believe, and I don't know this for sure, but I believe once Isaac Newton got this far, he just guessed the pattern. And I'm going to tell you one more. I'm going to give you a hint, and then I'm going to ask you to guess the pattern. Isaac Newton did do f of x equals x to the 1/2 power. That is also known as x to the square root of x. X to the 1/2 power, in other words, is also known as square root of x. And so Isaac Newton found out that the slope of square root of x is 1/2 x to the minus 1/2 power. Now, if you are a person that loves puzzles and are mathematically inclined, you should stop. You should just pause this video, and you should figure out the pattern. And here's the pattern I want you to figure out. If f of x equals x to the any power n, what is f prime of x? What is that pattern? Now, if you don't like puzzles, just keep on watching. Right? But if you love puzzles, stop right now. What is the, if x is raised to any power n, what is f prime of x? If you can decipher that pattern, you have discovered the power rule in calculus. So, in physics, you don't have to know how Isaac Newton invented the power rule. All that you have to know is what the power rule says. And what the power rule says is, if you have f of x equals x to the any power n, and n could be any number, actually it can't be any number, let me think. Yeah, no, n can be any number, any real number. So you have an equation and x's to the any power. It's very easy to give a new equation for the slope of the given equation, and that's, if you have any power of n, you take that power n, multiply it by x, and then you subtract 1 off the original power, and for any equation, that will tell you, for actually any x to the n equation, that will tell you for any given x the slope of that equation wherever you want to plug in the number x. So let's say you have f of x equals x to the 43rd power. You can do any power of x. X to the 43rd power, all you do is you take this 43, you write it out in front, and then x is to the power of 43 minus 1, otherwise known as 42. So notice, you can do any power equation. You can even do negative exponents. Let's say you have f of x equals x to the minus 2 power. Then you know f prime of x, or the derivative of x to the minus 2, is you take the minus 2, you put it out in front, and then you subtract 1 off of minus 2, and minus 2 minus 1 is actually minus 3, so the power rule works with negative exponents as well. It also works with fractions, but you have to know how to subtract 1 off of a fraction, but it still is true for fractions. Now here's a wonderful case. What if f of x equals x to the power of 1? That's just f of x equals x. And so what f prime of x is it's going to be 1 times x to the 1 minus 1 power, also known as 0, and x to the 0 power is also known as 1, so it's 1 times 1. If f of x equals x, and you have to just assume the power is 1, the derivative of x is always going to be 1. All right, another important special case is what if f of x equals 1? There's no x in the equation, so f of x just equals 1. How you should think of that is like this. 1 is really x to the 0 power. Any number raised to the 0 power is 1 from Algebra 2, maybe Algebra 1. But now, you just write the 0 out in front, 0x to the 0 minus 1 power. If f of x equals 1, f prime of x is going to be, well, 0 times any number is 0. So if f of x equals 1, f prime of x is 0. And actually, if you had you stopped and think about it, you would know this already. Because remember that f prime of x is the slope of f of x, and what f of x equals 1, this is a graph of f of x, and this is x. F of x equals 1 is a horizontal line. The slope of any horizontal line is 0, so the power rule actually tells you the truth. Alright, so as far as physics is concerned, what you have to know for physics is you have to know the power rule. If you didn't quite understand where the power rule comes from, that's nice to know for as a human being. You should know the wonders of calculus. That's part of our culture. But as far as just learning physics, you should know that if you get any equation where it's x to the any power n, you should be able to tell me an equation, f prime of x, what is the slope of the given equation. That process, incidentally, is called finding the derivative, and that's the important stuff to know in physics. Sadly, if you're taking calculus now, this kind of spoils the surprise for a lot of problems, and pretend that you don't know this, because your calculus teacher will be sad. This is a famous, oh look, and this is the famous punchline of the joke that I just ruined for you for all of calculus. And so just play along with them, because it makes math teachers happy when they can tell you the happy ending. That's how, so pretend you don't know the happy ending, but we're going to need to know this for Chapter 2 right away in physics. So the next video is just going to be other tricks. I think there's six different equations that you're going to need to know the equation for the slope of, and a couple things to do. What if two equations are multiplied to each other? What if two equations are added to each other? And that's going to be the next video. And those are going to be the important parts to what you have to know for physics. And of course, there's going to be little easy quizzes on the history of calculus, but the real meat of the stuff is going to come up in the next video.